So for this section, I'm going to be talking about the natural base e, which kind of plays into these exponential functions that we've been working with so far in this chapter. So e is considered to be an irrational number, and this is the approximate value of e right here. So remember, irrational numbers means that they're decimals, but they have no pattern to them. They have no repetition. Another famous irrational number is pi. And so e is kind of just one of those irrational numbers that gets used a lot. And they're used mainly in these exponential functions. Sometimes they'll be using e as the base of the exponential function. So a couple of examples would be like y equals 2 times e raised to the x power, or e raised to like a negative x, which would then cause it to become a fraction. The general graph of a function like y equals e raised to the x power looks like this. So e, remember, is about 2.7. So I'd be about there. And so my graph is going to just kind of gradually go through, and it's going to be an exponential function that looks something like this. Now remember, as it goes like towards the left, it's going to continue to try to go as close as it possibly can to that x-axis without actually ever crossing it. And this one would be going up. Now there are also cases where it would be going down, so that's kind of when we talked about exponential functions having like growth or decay. So let's practice just graphing a function that uses e. So like this first one, I have y equals e raised to the x plus 2 power. So to get started, we're going to create an xy chart. And we're going to put in numbers like -2, -1, 0, 1, and 2. Now you will need a calculator to evaluate this since you want to use that E button that's programmed into most calculators. So you're going to be putting these in to the x, which is in the exponent, adding it to 2, and then raising e to that power. So the first one, e raised to the -2 plus 2 becomes e to the 0 power, and anything to the 0 power is always just a 1. -1 is going to be e then raised to the first power, which would just be itself, and I'm going to round these, so 2.72. Again, that would just be e itself, but it would be an irrational number. I'm going to finish filling out my chart here, and again, I would go ahead and just round your numbers to make it easier on you when it comes to graphing. And you don't even have to round it out to places like I'm doing. You could just go to the nearest tenth if you wanted to. Okay, so you can see how quickly these numbers are growing, and that's because this is an exponential function. So when I go to graph it, I'm not going to have room to do all of these, but we should be able to do just at least the first couple and kind of just show the general shape of the graph. So -2 is at 1, -1 is at e, 0 is at 7.39. So about there. And then 1 is going to be too far off of my graph. So you can see if I were to connect these points, that eventually it's going to just shoot straight up so quickly, and like the next one's going to get bigger, and they're just going to continue to increase over time. Okay, if you want to give this one a try, go ahead and pause the video and try to do this one, and then when you're ready to check your work, go ahead and hit play, and I will be going through the problem. So I'm going to go ahead and set up my chart first. Now I'm going to use the same numbers that I used last time. And I got 2.9, 2.6, 2.3, and -4.4. So this one's a little bit slower when it comes to its movement because we're taking 3 minus the function raised to the exponent. So now I'm going to graph. Since most of these are very close together, we're not going to see a ton of movement happening here, and we're also going to have to estimate all of our answers. Okay, so that would be what that graph looks like there. Now we're going to look at E being used inside of logarithms. So remember from a previous section, we talked about some of the basic properties of logarithms that we can use to simplify bases. And one of them was when you had a log with a base and then the term or the argument piece matched what that base was. And so we were able to basically cancel this off and just grab the exponent x, whatever that is. So it could be a letter, it could be a number. Now we can do the same thing with these logarithms, but when you're dealing with E, it changes to what we call the natural log, and we use ln to represent that. So this is the natural log E of negative 2x. And so what this really means that I'm doing the log base E with my E being raised to the negative 2x. So these two quantities are interchangeable. Like you can go back and forth between the two of them. So what's happening here is that the log E and E are going to cancel each other off and you're left with just that exponent. When you're looking at the natural log of E, it basically does the same thing where this is going to cross off and you're left with just the exponent. And so that's going to be our answer for this one, negative 2x. So for number 2, you can basically cancel that off and you're left with 3x. Okay, so that was the first property that we talked about. Now another one that we went over was when you had a base raised to the logarithm with the base. And so again, kind of like the main thing here is to make sure that these things are matching, the b's, whatever those numbers might be. And so again, we can kind of think about those being canceled off. And so we're left with just that x or that exponent. Okay, so when you see it with E being raised to the natural log, again, what this means is that if I was doing E raised to the log of E of my quantity t minus 1. So now these, again, are interchangeable, and I can basically cross off E raised to the log E and E raised to the natural log, and I'm left with just that exponent quantity, t minus 1. Now for number 2, before you try to cancel things off, because we have this 5 sitting in front of the natural log, we talked about a power rule in the past, which is when you take this 5 and you put it up with the exponent into that position there. So this is really E, the natural log of x to the 5th power. And so those quantities cancel each other off, and we're left with x to the 5th. Now for number 3, because there's a 3 sitting in front, I would mainly just focus on looking at the natural log E portion first. So think of these two things crossing each other off and you bring down the x, but since you have this 3 sitting in the front, you're also going to have to bring the 3 with it as well. So your answer is going to say 3x. So if you're multiplying those two quantities together. So that just kind of shows you how some of those properties that we've talked about in the past are directly related to this new kind of idea, which is that natural log or using that E as the base. What I want to finish up with here is just doing some extra practice with solving logarithmic equations. And there's two main ways to solve them. The first one is that sometimes the logarithms just drop out. So we had seen this a couple sections ago, where if you have logs with the same base, you can essentially get rid of them and set their arguments equal to each other. 3x minus 11 equals x minus 3, and then you just solve for your x. So for this one, I'm going to subtract x. I'm also going to just go ahead and add 11 in the same step, just to get both of those terms kind of moved around. So my x is gone, and my 11 is gone, and I just have to simplify what's left. So 3x minus x would be 2x. Negative 3 plus 11 is going to leave me with an 8, and then I divide by 2, and so x is going to equal 4. Now for this one, because we have these numbers sitting in front of the logarithms, I would first start by moving them so that they're exponents. Like so. Now you can go ahead and drop off log 8. And so if we simplify, we have x to the 4th equals 9 squared is going to be 81. And then we have kind of this fourth root is what we're doing to both things here. So we're thinking like what number raised to the 4th power equals 81? And you're going to get 3. And really, you know, there's like a plus minus here, because anytime that you square root something or anytime that you root anything, there's a positive and there's a negative answer. But we've talked in the past that if you have negative numbers or if you have a 0 in a logarithm, it does not work. So I actually have to throw out the negative 3 answer and only take the positive 3. Because if I try to do log base 8 of a negative 3, it's not going to work. I'm going to get an error message. So that's one way we're solving these where they just kind of drop off. The second way is when we want to rewrite it so that it's an exponential equation. So you might have to do some simplifying first, and then if you can't get just your logs to drop off, like in this first one, the only reason why I can't drop off the logs right away is because 2 does not have the log 6. So I'm going to simplify this and then rewrite it as an exponential equation and then solve. So for this one, because on the left side I am adding these two logs together, that means that I'm going to multiply those quantities, x and 3. So it's 3 times x, or 3x. And this is going to equal 2. So then what I'm going to do is rewrite this as an exponential function. So you take that 6, 2 becomes the exponent, so 6 squared equals 3x. 6 squared would be 36. Equals 3x, we divide by 3, so x is going to equal 12. If you want to try to do this one, pause the video and then come back and hit play when you're ready to see the solution. I would advise you that after you find your answers that you check them and make sure that they don't cause any problems or you don't have to throw any of them out. So the first thing that I did was move this 2 so that it became an exponent. So it's the quantity x plus 6 squared, and then minus log base 2, 16 equals 2. This one has a subtraction sign, which means that we're going to divide. Then I'm going to rewrite this as an exponential equation. So this becomes 2 squared, using this 2 and this 2, and I'm going to set that equal to that x plus 6 squared over 16. And what I'm going to do here is actually square root everything. Now when I square root the fraction, remember it's like a big square root is over the whole thing, or you can think of this as like having individual square roots. If you need to write them out individually so that you remember to do both of them, I would suggest doing that. When you square root something that has an exponent of a 2, you basically are canceling them out. And so you're going to be left with just a 2 over here. And on the right side, you're going to have x plus 6 over 4. So on the left side, make sure that we also put our plus minus sign. And so now we're going to solve. I'm going to first start by multiplying by 4. So it's going to say plus or minus 8 equals x plus 6. So we have two options here. We have positive 8 minus 6, and we have negative 8 minus 6. Positive 8 minus 6 is going to leave me with a 2. Negative 8 minus 6 is going to leave me with a negative 14. If we come back up here, remember when I plug them in to my logarithm, and this was the one that has the x, I cannot have a negative number. If I plugged in negative 14 for x and I added 6 to it, I'm going to have negative 8. That logarithm is not going to be able to be evaluated for a real number, so I have to throw out the x equals negative 14, and I only take x equals 2.